Salutations 216ers, this is Professor Kaufman, and what ensues will be our final project overview video. It is for Project 5, which concerns performance optimization, threading, and virtual memory management. It has you implementing a small version of malloc. As you can probably see from the project outline, there are two problems here, and both of them are relatively short because they involve either writing code in a very limited circumstance, as is the case in problem 1, where the code's not very long and it's divided into some required functions in a template that's been provided to you, or just writing a single function, although you'll probably spend some considerable amount of time on that function in problem 2, as the point is to optimize the performance of an existing version. Let's take each of those two in turn. So the nature of the first problem is outlined in the section that describes it, and it will have you implementing your own little version of a memory allocator, which is more or less the class that malloc and free fall into. The particular kind of memory allocator that you're going to implement here, it manages the heap by overlaying a data structure on it. And a commonly used data structure, at least in some heap implementations, is just a doubly linked list that's there. Thus the name lmalloc, which is an abbreviation for an explicit list malloc. There are implicit lists, there are versions that manage with trees, there are hybrid approaches, which is actually the GNU's libc version that has some explicit lists, but also some other things that are done there. But this is a good sort of introduction to it. The essence of this is then that the heap is managed as one big block of memory, and overlaid on it are two lists, one which has the available blocks that could be granted via malloc, and a second list that is the used set of blocks. Now, in reality, if you're trying to do this efficiently, you'd probably forego the used list. It's not as needed. But it's useful in these cases in a learning setting like this because it makes it easier for you to see what's going on. So tied up in the discussion of the project then and its implementation will be a couple of data structures that are worth noting. First, the heap's going to be divided into blocks. And this is generally then as you would grant a request from like malloc. There's some data that's provided via the void pointer that malloc produces, but also some data that surrounds that block that pertains to the bookkeeping operations that the memory allocator has to keep track of. And so a block, which will be a central data structure in here, has two parts, a head that appears before the memory that's granted the user, and a little foot that appears afterwards. Within the head, there'll be a mention of how many bytes big the block that follows it is, what state it's in, whether available or used, and then a couple pointers that pertain to the linked list that are around it. So here's a picture of what a block sort of looks like, with in blue the header portion and the green the footer portion. You can see, they're not terribly complicated, but as you would malloc something, such a block would be created via some fashion, and we'll see how in just a second, and the user would get a pointer to the stuff that's in between here. So if they called malloc of 16, then this might be what's returned is a pointer to this little gray area here. I forget, this goes by a couple different names like payload or the user area or whatever. The point is then that one of these structs over here precedes it, and one of the structs here, the footer, that follows it. Each of these encodes the size along with some other properties, and the fact that the footer is 16 bytes big is going to allow you to zip back past this and subtract off of a pointer to a footer, for instance, the 16 bytes that are here plus whatever the size of this head is to find this thing. And conversely, this header could add 16 bytes from its end to find the footer over here, or go a little further to find an adjacent block there. So there are a couple different competing concepts here. The heap is going to be laid out as a series of blocks here, but then the blocks will either be in use or available to be granted via malloc. And the pointers here, the previous and next, they'll pertain to the list, either the available or the used list that's on there. So this becomes a little bit easier to see if you get a more global view. So I'm going to zip down to this picture, which represents, here's the giant block of memory that is the heap. And it is divided amongst blocks that are either in use, and those are marked in gray here, and those that are available that could be used to grant a malloc call. And those are marked in yellow over here. So these two different lists here, available and used, they're part of a single global data structure, this L control, which you can have a look at in the header file in a second. which tracks global information about the heap. And the heap is sort of a singular global data structure in that respect that needs to manipulate these little lists as things come in by way of mallocs and frees and so forth. So if this is the beginning of the heap, the memory address at which it starts, and this is the end heap over here, if you scan just linearly across this, like if this memory address 10,000, then you go up a ways, you find another block, you go up a little bit higher up over here, and this would be the end of the heap, so maybe it ends at byte address 11,000 or something like that. As you scan across, you'll see a sequence of used blocks that are marked in gray and yellow available blocks that are over here, but they're interspersed with each other. Anything that has been granted via a call to malloc has been returned to the user by a call to that. It would be lmalloc in our case rather than malloc, but I'll just say malloc going forwards. So that the user in their program, perhaps in their stack or in their data structures, they have pointers up here to those gray areas because they'll maybe put an array here or a struct here or some data over here that's needed, etc. The yellow ones don't have any pointers from the user program in it because they're currently available. Perhaps they were allocated and were freed, or perhaps due to the allocation scheme, like there was a gap over here. But if someone asked for some additional space, say they wanted 50 bytes or so, then the general approach would be to say, which are my available blocks? And I'll follow a link that I have at the beginning to that over here, and it goes directly to the first yellow block that's over here. And if one is asking for 50 bytes, then you look at this available block. It has 22 bytes in this yellow area. That's insufficient to grant a request for 50 bytes. And so you'd follow the next link on this and find the next available block only has 16, so that's not big enough. And then find the next link over here, which this one does have 100 bytes in it, so it would be big enough to grant an allocation of 50 bytes. Now, to do so will involve splitting this block to say, well, it's got 100 in it. There's no reason to give away the whole 100. Instead, I'll divide this yellow area and create a used block now, like a gray one, that is 50 bytes big. And whatever remains, I'll use to create a second block over here, which has whatever remaining space that's induced. Now you can see in between any two blocks, there's a combination of a foot at the end of the earlier block in memory and a head that's the start of the next block, with the exceptions being the very first block in the heap and the very last block in the heap. And so anytime you'd split a block like this, you'll induce some overhead because in this yellow area, that can't all be used to grant user requests. Rather, it must also be used to put a head and a foot in the middle here to divide the block into stuff. And so the heap's going to start out as one big yellow chunk, and as you would malloc things, you'll split off little gray slivers along here. And along the way, perhaps someone would call free on it to say this was gray, and it'll move out of the available list, out of the used list and back into the available list over here. So this is the essence of what's happening, and we'll have to talk about a few mechanics here, but generally then heap management becomes the fine art of managing a couple doubly linked lists, and as well then splitting blocks off to increase the number of blocks that are available, or remerging them as they become both available again on freeze. We'll talk about those things as we go forwards here. So, with a bit of context, then it's worth pointing out then the global control parts here. There's a predefined type and global data, bit of data, the L control type, and this has then the fields that are necessary to follow to find the available and used lists that I mentioned down here. And those are encoded via a doubly linked list over here, the L block list. And it has a few peculiarities to it that you'll encounter, but generally is sort of a normal looking linked list of the blocks that are in here, which we already talked about up here, have these little links between available and next. An important distinction I want to mention once more, and this will come up over and over, is that the things that are in these list links, they do not point to the immediately above block over here. So there's a difference in the notion of the next block, because that will return to either the next in the list that I'm in this case this not available, this used block, has to chase and skip over this one in order to find the next used one, then the next used one, and the next used one, and so forth. Versus there's also whatever block is directly above this lowest block here, which is this available block there. So it's the next highest block in memory, which you can find just with some pointer arithmetic. You have a pointer to the head here, then you can move up one block by adding 256 bytes to where it starts, plus the size of a footer and a header. I think those are described as the overhead there. because each block has to have both a head and a foot there. And so by doing a little pointer arithmetic, you can sort of navigate this linearly. You'll see in the test output for various tests associated with this, both displays. Perhaps early on, it will see here's the way the heap is arranged from the earliest blocks that are in it to the latest blocks. And as well, then later on, you'll also see, oh, here's everything that's in the used list. So starting here, and then here, and then here, and then here. That's the end of the used list. And the available list is all the yellow ones in sequence as well. Those two are distinct, but they're both important as you would develop code for this, as they both have a place in terms of the semantics and functioning of the heap there. Of course, if you wanted to, grant a malloc, you'd have to search through only the available blocks, because I can't very well grant the user this block here that's already in use. If they're asking 50 bytes, it's already been granted to them once before. So I have to restrict attention to the yellow blocks that are over here. Okay, so let's, another facet then we're going to talk about is if this block, this gray one, turns to yellow, you can see I've got 3 little yellow blocks in a row, and I want to merge those. So we'll talk about that in a second. So these pictures can be extremely useful in understanding the overall operations and then some of the specific mechanics of some of those operations. For example, among the first functions that you'll need to write involve moving around in the heap linearly. So here I've got a couple blocks arranged. They've got pointers to different spots over here, and you can see the pointer for this next block, it points over and beyond the immediately adjacent block in memory. And that's because it would never point to this gray one if it's an available block with 16 bytes. Then it would point to the next available block over here. Not necessarily linearly in order, and we'll get to sort of discussing that part as well. But rather just some other block in the list of those that are available. Likewise, this used block right here will point someplace else to its another used block, and then point backwards to some other previous used block over there. Would never point to this yellow one over there. However, it is useful to say, okay, this available block, let me move up 1 block over here. And again, that can be done via pointer arithmetic. That this little yellow area, it is 16 bytes big. It's variable in size, so 16 here, 8 here, etc. However, the blue and the green, they are structs. And so as all structs are in C, they're fixed size. And so I would just add 16 plus the size of a blue area of head plus the size of a green area here. I could go from this first pointer over here to this next one over here. And conversely, if I'm looking at this block over here and wanted to go down 1 to find the block that's beneath it, block below, as it's called, then all I need to do is to say, oh, I don't know how big the thing is beneath me, but I know right next to me over here is a foot. And so a little pointer arithmetic and say, find a pointer to this foot struct. I'll grab out that 16 and say, this pointer, this block header pointer here, minus 16, minus the size of a foot, minus the size of head, and voila, I'm down here at the bottom of the thing. That's why the size is stored both in heads and feet here to allow navigation in either direction. If I didn't have a foot, then there'd be no way for this upper block to figure out how do I move down 1 block over there. And that'll become important later on. So among the first functions that you'll need to write is find the preceding block foot, find the preceding below block. I believe that's L block below, the first required function to implement. Finally then, later on as you move through the project, you're going to have to deal with block splitting and merging. And so as some request comes in to malloc something, for instance, I would, let's see, the request here is that I want to malloc some block that has 60 bytes in it. Is it 60? Yeah, 60 bytes in it. I'm trying to think here. Is this right? Yeah, sorry. I'm just confusing my examples. This has actually 2 examples of it. So then it will be necessary to find a block and then split it. So the split operation looks something like the following, that you'll navigate through all of these yellow ones until you find one that has sufficient size for it. And this will be a block that is big enough to say, oh, it's got the 60 bytes I need, and it's also bigger than 100, which is the size of 60 plus the size of a foot plus the size of a head plus a foot over here. And so the splitting process will say, okay, I've located this block. It's the first one I found that qualifies. And what is to be done is to take this little middle section here and just establish a foot and a head there. Now, this can feel a little bit weird because this is just sort of raw space, it's a bunch of bytes, but C allows, as many languages don't allow, you just say, no, pretend that some set of bytes in here is actually a foot. So cast as a pointer and then assign it as though it were a number, that this is your new size, 60 bytes. And immediately after that, cast a pointer to say, point right here, and say, that's a head now. Now, it wasn't before, but keep in mind, they're just bytes here. And all we've done is to shift encode the interpretation of those bytes as raw space to encoding a struct of some kind. And that's all that's needed then to split it in this way, so long as you make use of the other data structures to track this. So plopping down the desired size 60 here and establishing a new head over here that has the remaining size. That'll be subtract off the 60 and subtract off the size that you need for this foot here and this head here. That'll be, I can't remember exactly, but it's size of structs there and encoded as the overhead, the size of a foot and a head combined over here, which I guess is 40 bytes. I mean, it's actually pretty costly compared to modern implementations, but easy enough to implement here. So establishing that then leaves 200 bytes left. So I'll modify this existing foot to say 200 there, because it now belongs more or less to a new block. Encode that size over here, and then return the fact that, okay, this is now split off, and the block that I was pointing at has shrunk apparently down to 60 bytes big here. Now, in some cases, if the sizes are not sufficient to establish and actually properly do a split, then you just end up returning, okay, the size that was there, you can not modify that at all and indicate that it's actually exactly what it was. So it's big enough for the 60 bytes, but what I will return is a block that's 80 bytes big because I couldn't split it, didn't have enough space for the overhead there. So there's a somewhat more detailed example then later on about how to completely fulfill this objective of mallocating. That early on, what you'll do is a search of all of the blocks over here until you find the first one that meets the proper criteria. In this case, this 300 bytes block here. And then go through this splitting business. And say now on the request of 60 bytes for some block, I'll have split off this one. It's now moved away from the available list into the used list there. However, this freshly created block, which was up here, that's 200 bytes, it remains after I peeled off this piece over here, then I'll reestablish that as the front of the available list. So even if it wasn't the earliest thing that appear in memory that's available, by virtue of the fact that it's now split off, then the first thing in the available list becomes this. Those are semantics that make it easy for testing then. I don't have to worry about doing any searching to where to insert it, just insert it at the front of the list, the most efficient place to insert it in any kind of list for that matter. So at any rate, this is the basics of doing an malloc. The counterpart to that is freeing blocks. And the essence here is just to return a block that's in use, such as this middle gray one, return it to the available list. So barring any other considerations, this is a 60 byte block. Some user said, oh, I've got a pointer to this, let me free it. And that will in turn move to the process of like, okay, to this thing, let's shift it over from used here to available, and color-wise, this changes it from gray to yellow, and I'll need to then insert it into the list of the available. It becomes the first one in that list then. So again, won't necessarily appear in the list in order as they would appear in memory, but the most recently changed block in that respect goes to the front there. Now, you can see there's not much else to do here because adjacent to this block are a couple used blocks and not much can be done. However, in the events that you freed the block in this situation, you see, oh, there's actually, that would make two yellows in a row here, an available block and an available block. Now, if someone comes along later on and asks for, I'd like a block that's 150 bytes long, then that's no good because not big enough for 150, not big enough for 150, but their combined size would be. And so the basic strategy is on freeing this middle block right here, you look around and see, are there any adjacent yellow blocks that I can merge with, coalesce as the word goes sometimes. And if looking backwards, you find, oh, the block beneath me is actually available too, then it makes sense to merge into one bigger block. And so that process would be this block right here. As you free it, you change it to yellow, and then jump one down using that handy-dandy block below function that you wrote to say, is this one also available? If in fact it is, then you eliminate this header in the middle, this footer in the middle, and to say this is now a block that is 190 bytes big. So that's the 90 plus the 60 plus the overhead of that is incurred by having a divider in here. Just pretend that's not a divider anymore. That rewrite this one so that it is 190 bytes big, both in the header and the footer. Insert that into the available list, and voila, you've just merged some blocks and have a bigger space. Someone comes along later and says, give me a block that's 150 bytes big, and now this one can be used to grant that. In fact, be the perfect size for that thing. All right, so I think that's the essence then of the operations, at least in pictures, to be written. Let's just take a look at the code quick, as it's present in a template file, and then we'll come back to the spec in just a second. I'm going to grab this link over here, copy that, and then jump over here to my sync. I'll do a little wget to grab this thing out. If I refresh over here, I've got my P5 code, so I'll unzip that. And then if I jump in here, you'll see the files that are provided. We're dealing with the first problem, which is in lmalloc, and primarily you'll be editing the code that's in lmalloc.c. If I open that thing up and start zipping through, you'll see there's actually a lot in here already. I'll make a quick mention that our friend mmap, the memory mapping function that manipulates the page tables of the operating system, that's in use here for provided code, and it'll also be something that you will need to make use of later on as we talk about expanding the heap. But for now, you can zip around and sort of look to get oriented. I'll call your attention, though, to the fact there are some functions that are marked as required. And these are the functions that you will need to implement that presently don't do squat. And so you maybe just work through here and say, oh, there's a required function. I need to understand a little bit about what this is. This is given a foot, find a head. Down here is a required function. Get the block that's below this current block that's over here, and so on down the line. There isn't a ton of rhyme or reason to the required functions, their placement in here. They're interspersed with things that you don't need to implement. So just be aware that you might have to do a little searching and find that Control F to say required. Oops, if I can spell it. And sort of zip through and find all of those as you go. So to that end, you just start filling in definitions for functions. Make sure you have a reasonably good idea of what the intent of the functions is, and look for the documentation comments that are given here and additional explanations in the project specification about that. And you shouldn't go too far wrong. Okay, other things I want to mention. So the heap, as it would start out, has somewhat of a fixed size that's over here. And you can see in some of the provided code here that fixed size is dictated by the memory mapping that's done. If you recall, mmap allows you to map memory into the virtual address space of a process. And this is basically granted from the operating system is this stuff that I'm giving you is now in bounds. There's a pound-defined start address for the heap over here, and a pound-defined number of bytes that's required for the initial version of it. At any rate, so it's at the initial size over here. And so this provided initialization code, this will take care of that for you. You don't need to call it. It's called in the testing framework and so forth. However, what you'd notice then as you would run things is like, oh, the heap starts out, it's at a certain size, but if that size is not sufficient for the data that I would want to make use of, then you may wish to expand the heap. And the obvious thing to do in this case is just to memory map some more pages that are after the end address of the heap. Now that stuff is stored in some of the control data structures that are laid out here. So heap start and heap end. And if you map some pages starting here, then this will grow the heap. Of course, after that, you'd want to like change where the heap actually ends, but you'd have more bytes of space in there. You wouldn't want to map this at arbitrary locations, but rather if this address, well, actually I should pull it up here because I think that's the easiest way to see. You've got this lmalloc over here, and the heap is going to start at the address 612 and then 000 over here. So I map 2 or 3 pages that I'd see in this digit right here, like a 2 or a 3. And I think this is the initial size, just 1 page, this would be a 1. So if I mapped another page right here, I now have 2 pages. And so the heap would extend from the starting address to this 612 as like to 2 over here. And if I mapped yet another page, that'd be 3 over here. So you're required to write a function for this. Which is towards the end, append pages to heap, which is because how many pages you want, grow the heap by that number of pages, and all you need to do is a little bit of memory mapping to make this bigger. And that would make it possible then to allocate larger arrays, for instance, and it's not necessarily something that you would do manually, but rather on a call to lmalloc, if the space needs to sort of expand, then this could be done. I don't think that's part of the project spec, and it's not expected, but to expand the heap, then you would need to have this function available in some fashion. So a user would look at this and say, I'll try to malloc, like, well, it failed because there wasn't any block that's big enough in the heap. Maybe expand it by a few pages and then try again, and we're good to go. Normally, malloc would handle that for you, but we're implementing a sort of simple version of this here. Just get an understanding of how the virtual memory system plays to create the ability in a FreeC program to have something like a heap and dynamically expand it. Okay, I think that's as much as I want to say on the content. A few other items to mention that are important since I got the header up over here. You're going to be doing a lot of pointer arithmetic in here, and this is easy to mess up. And so provided to you are some macros that will allow for easy use of pointer arithmetic. Pointer plus bytes, pointer minus bytes. I don't think there's much of a use for this pointer minus pointer, but it's there. Generally, this does to say, give me a pointer and give me a number of bytes and add on to it. The casting is important there because, in C programs doing pointer arithmetic, normally the compiler will scale by the size of whatever is pointered at. So add 4 times whatever number you say if you're adding on to an integer pointer, or if you're adding on to a double pointer, then add on, multiply by the size by 8, because that's how big doubles are. In cases like this, where you're doing very direct memory manipulations, you don't want that scaling. It's like, this thing is 17 bytes big, I just want to go 17 bytes forwards from it. And so if you're looking for inspiration, if you have a look at some of the uses for this, you just see things like, pointer plus bytes. Here's a pointer. That's the beginning right here, and here's some number of bytes over here to add on. That'll do the raw thing instead of scaling it by whatever the size of this heap thing that's pointed to at there. And so make liberal use of that pointer plus bytes to make your code a little bit cleaner and easier to read, and to avoid the inevitable problems that come when you would improperly scale things in that way. Since a head is like 32 bytes big or something like that, if you just directly add onto it, it'll be 4 times 32 bytes, so that'll go a lot further than you really want to there. Pointer plus bytes will eliminate that part. And I think, that's about all I really want to say on this. It's a fairly, I wouldn't say simple project. It requires a little bit of mental flexibility, but will teach you a lot then. It's like, this is how malloc and free actually work. This is why it's hard if you would want to expand the size of an array. Here's my array, and it's sandwiched in between this guy and available block. I could expand it maybe a little bit if I could steal from this over here. But if my array started here, it's sandwiched against another malloc's stuff. So expanding that would corrupt the data that's over here. So I just can't expand an array that's over there. And this explains some of the semantics then of how malloc and free would work, and how in many languages, C included in that, but every other one I know, Java's and OCamls and Pythons as well, you can't expand this efficiently willy-nilly. There are ways around that, but they're more complex because you're dealing with a heap that's structured like this. Problem 1, lmalloc. Have fun with that. I should say in terms of code development, you can start filling in definitions, but this should compile if all things are equal just straight out of the gate. So you should be able to do without making any changes. Make test prob 1. This should compile and run. It'll fail all of the tests out of there, but that's no big deal in that respect. If you fill in a few definitions for the get header and block below and so forth, then you start passing some tests and quickly move on to the actual malloc granting stuff that's there. Okay, let us talk through then the second problem, which involves optimization. So the particular problem that you're going to optimize is one of normalizing some data. Normalization is a bit of a vague term. It could mean a lot of different things to a lot of different people. And so we're electing to use a sort of traditional statistical definition, which is to say normalized data, if you have a collection, like a big array of such data, if you figured out what their mean is, their average, it would be 0, and that the standard deviation is 1.0. So this is nicely centered at 0 with the little bell curve around it. I mean, there's no saying whether the distribution actually looks like that, but that's sort of the ideal out there. Now, why would one do this? In lots of machine learning applications, statistical applications, if you are dealing with disparate kinds of data, and for instance doing a linear regression on it or a neural network on it, you'll end up adding things together a lot. And if they're scaled very wildly different, like, oh, here is something that's measured in, if you have two length measurements, like one is measured in meters and the other is in nanometers, but they're both of similar length, like this is a meter and this is 1,000,000 nanometers. There's a lot of numerical instability that comes then from adding small numbers and big numbers together. The small numbers sort of lose their significance in that case because we're dealing with finite precision machines. So scaling them to about the same range then of centered at 0 with a sort of deviation about 1.0 means all of the different features that you could measure about folks, height, weight, age, GPAs, income for the year, etc. These kinds of features associated with samples. This becomes much easier then to bake into a uniform model as they're scaled in some fashion that will not affect your ability to predict because the sort of dynamic ranges are the same. However, the stability of the model is much better. You don't have to take my word for it. If you go on and take some machine learning or statistics classes later, perhaps they'll explain that in more detail, but it's a very common practice, and it makes for a good practice for us to sort out some other things here. So in case you've forgotten how to calculate an average and a standard deviation, there's some code here to repeat this stuff. And the essence of this is going to be there'll be a whole bunch of measurements that are encoded in a matrix. So here's a first measurement of somebody. It's like their scores on various exams, perhaps. And here's a second measurement of someone else. Their scores on a bunch of assignments and so forth. Apparently, they're not doing so hot if they're getting negative scores or something like that. Or maybe this is like above and below, like some common scores, something like that. Now, the idea then is that this column is the same measurement for a whole bunch of people. This column is the same measurement for a whole bunch of people. This column is the same measurement for the whole bunch of different people. Measurement of like height, weight, I'm trying to think of something else. Height and weight and age and income. I don't know, something along those lines. So we want to normalize across a column here. And so this 1.0 that's mentioned here is the average of, or sorry, minus 1.0 is the average of this first column. We can try to verify, so that's 10 here on the positive, so it's a negative 11, negative 15 for the positive, so that's a total here for this column of minus 5, and there are 1, 2, 3, 4, 5 columns, so yeah, the average would be negative 1.0. And likewise, this average over here is the average of each of the columns here lined up so that it hopefully makes it easy to sort of understand that part. The standard deviation as well is something that's calculated according to this little algorithm. Figure out what the average is, then go through and subtract this minus 6 minus the negative 1 would be minus 5. You square that, add it on to some sum over here. Do the same for all of these, and then take that squared sums and divide it by how many are, then take the square root of that, and you've got your standard deviation, which, if you believe my math, is 5.7. So these two properties are for this column, these two for this column, etc. Finally, the last act is to normalize this, which is subtract off the mean and divide by the standard deviation. So this normalized matrix will be computed by taking this first entry, adding 1 onto it. That's subtract a -1, which is just adding 1, and then divided by this. And that should get minus 0.88. Likewise for this, subtract off the same mean to divide by the same standard deviation for the column. And likewise for the -9 that's up here, it has a different mean, so subtract off the minus 3.20 and divide by the mean over here, etc. down here. So each of the numbers over here are the average and standard deviation for the column. That should give you this resulting matrix, which, if you were to do so, to calculate the average and standard deviation again, they'd be 0s and 1s across the board. So they're all scaled in sort of the same range in that way. To that end, then, this is now a normalized matrix and would be much nicer if you fed it into some SciPy or scikit-learn or something like that. At any rate, there's an algorithm given for this, this call norm base, and it follows exactly the hand-wavy algorithm that we just used, like go down some columns. So for each column, run down that column, calculate a sum, divide by how many rows there are, that gets you the average. Run down the column again, getting out the matrix elements, subtracting off the average, squaring that, and summing it, and at the end, once you've got all those computes, here's the standard deviation for that column. And then go through and subtract and divide off the average, divide off the standard deviation, and change the matrix element to be the new element, and voila, you've normalized it. Now what sucks about this algorithm, I mean, it's great because, it's exactly what I do as a human for it. If this were a small matrix, if I was a large matrix, I would write some code to do this, but this would not be a good set of code to use. It would get the job done. It would compute the correct results, but it is slow. And anyone who's tracked the last, 3 weeks of class or so should see an immediate suspicious element here of iterating in the outer loop over columns and the inner loop over rows, which means I'm going to go down columns. Now, if that doesn't ring a bell as, that's not great for performance, and I'm not sure why, it's a good time now to go back and review some of the past class topics as we address this issue very, very readily in several places, including in lecture and in lab and possibly also on homework and so forth. So go back and solidify why that's a bad idea and what alternatives are for it. Because your job is to take this baseline version and kick the snot out of it. You'll to write an optimized version of this in call norm optim, and we'll talk a little bit in code about how that might look, and then run a benchmark that's provided on Grace preferably, although you can sort of do your development at home first if you want, and see how much faster your version goes than the version that's provided over here. So a couple things to note, this is a performance exercise, and so the performance is actually tied to some specific set of hardware. And the best common grounds that we have for you to test this on is the Grace nodes. Irritatingly, not all the Grace nodes are created equal. The even ones have slightly crummier processors than the odd ones. And so your evaluation should be done on one of the following 4 machines, Grace 3, 5, 7, or 9. They all have the same CPU and memory setup in them. And so you'll at some point want to SSH into those systems and run the benchmark that's provided. Concerning the benchmark, the outputs for it looks something like this, and I'll just scroll down to one of the sort of quintessential examples. When you run this on an even or an odd Grace node over here, it's called call norm benchmark. It's going to run first the baseline version, and then your optimized version, and then compare the speed up, which is just how long this took divided by how long this took. So I got a little bit of speed up here, and then later on, for this bigger matrix, 4,099 rows by 8,197 columns, it took about 2.5 seconds for the baseline, but my version here took about 0.3 seconds. So that's an 8x speed up, which is pretty good. The number of points you earn is directly correlated to this. So since it was about a 3x speed up, I got about 3 points out of it. And that on my total went from 7 to 10.27 over here. And you can see the points for each little part of this, along with the total that's accumulated over here, getting up to about 32 points total. And 35 is the sort of full credit score on this thing. If you exceed 35 by a little bit, then it's just rounded down to 35. So that's there. Now, a couple important aspects of this. You need to run this on Grace 3. If you run it at home, you'll get a bunch of warnings. If you run it on even Grace node, then you'll get a bunch of warnings over here indicating that The benchmark scoring is tuned for specifically this odd set of grace machines, and so if you run it elsewhere, your results could be wildly different. For instance, running it over here on this even grace node, I got like a very pitiful performance, and that's undeserved. Rather, I would want to run it on the even or the odd numbers, and I get something that looks more like this over here. So feel free to develop your code, see if it compiles like wherever you want. Just know that the scoring that will be used eventually is here on the odd grace nodes. Now, in terms of us actually assigning credit for this, when you submit to Gradescope, that's also not grace. And so there won't be any report of what are your performance numbers on Gradescope. Rather, later on, after the submission window closes, graders will download your codes and run them on Grace and on the odd nodes, and that will then be used, sort of the best of 3 runs. We'll run it 3 times, and whatever your best score is, like that's what we'll assign for your performance part of this. So unlike some other projects, you won't know exactly what your score is in this until our graders actually come in, so it's more of a normal assignment in that respect. So, but you can get a pretty good sense of this as you would run this multiple times on the grace, the odd grace nodes there. So be cautious about that. Don't get caught off guard. Let's see, I think we've talked about all the stuff that's over here, and sort of I've reiterated over and over. Make sure that you're doing your sort of final assessments of this on the odd grace nodes and so forth. So it's very likely, another thing I should mention while we got the benchmark up. So in addition to the other optimizations that you're likely to want to perform, one of the things that you'll be required to do is to multi-thread this, as this is the last technical topic of the course. You can see over here a little TCOM, which is an indication of your code gets called with a parameter, the number of threads or thread count or something like that. And so this will go on the benchmark from 1, 2, 3, and 4. And using multiple threads then gives the opportunity to potentially speed things up. In this particular run, which is only a partial credit run, you can see I didn't get any speed up through the use of threads here. It might be because the cruddy implementation I use here didn't actually use threads for anything, but still got reasonable speed up even without that. Down here, the full credit one, as the number of threads increased, not necessarily linearly, but I got more bang for my buck by using multiple threads out there. And so this is the key then to getting full credit over here, 39 out of 35, which is then rounded down here. So optimizing the memory performance and as well the use of threads here is going to be the key to getting full credit on this. If you significantly exceed 35 points, there is some bonus credit available, and you'll sort of know it when you get it there because the output for the benchmark will change subtly, or not so subtly, and that to indicate you've earned some makeup credit there. So feel free to explore those optimizations. Now, in the process of developing this, and you can see it's not a terribly long function as the baseline is provided, your versions will probably get somewhat longer there. So there are a couple of things associated with that. It's easy to introduce bugs into the situation, and so if you ever get wrong results here, as in, I computed this thing, I computed it really fast, but it was incorrect. It did not match what the baseline numbers were. So if the matrix is wrong or the average is wrong or something like that, then this is something that will eliminate all credit for that run. So incorrect results are, sink your score to 0 at that point. You'll get tons of little irritating output messages there that we'll see in a second to indicate, yeah, you haven't earned any credit because you produced wrong results. As my old boss used to say, I can write extremely optimized code as long as I don't have to produce incorrect results. I'll just return a random number or return 0. That'll be done very fast, but it's probably not what you're interested in. What you want is optimized correct results, and that's our goal here. So as you encounter problems with this, it's handy to be able to debug a little bit. The benchmark is a rather large, unwieldy bit for this. So there's also a call norm print function, sort of routine that's provided, program that's provided, that will similarly call the baseline version of your code and the optimized version that you'll be writing, and show what are the results on small matrices. So in this case, running on a 5x8 matrix, it'll show the entire matrix over here, and then run through and say, the baseline version computed for this 0th column over here, a average of minus 2.0 for the 1th column here, an average of 3, and over here the optimized version, the code that you're to write, it produced exactly the same thing, within a small margin of error, 3 and so on. Same thing for the standard deviation over here, and then the normalization of the matrix is long and tedious over here, but matches largely. Now, should you see errors over here, as like some average element's wrong, some matrix elements wrong, then it would be a good idea to run this print program on some small matrix. For instance, over here, as I would run it on this little 4 by 5 with 2 threads, so that's the last parameter over here, you see something went wrong where I'm getting nans for the averages over here, and the output over here indicates maybe the matrix, I forgot to normalize it or something like that, but something's definitely going wrong here. All of the elements that don't match what the baseline is, they're marked with these little stars over here. And so this can help to sort of, if you encounter problems, if you do some optimization that screws things up, maybe rerun that on the little call norm, the print here, and see if you can suss out for small size matrices exactly which ones are going wrong there. Okay, there's suggestions for optimization over here. For instance, you'll definitely want to optimize the memory access pattern to favor cache. That will give you the most bang for your buck, and if you fail to do so, it's likely that anything you do with threads won't work out so well. By way of threads as well, then you'll need to split up the work to be done on the matrix amongst a bunch of worker threads. And we'll be talking in lecture about that, and the subject of this week's lab, Lab 12, also pertains to how you divide up work using threads and coordinate them using mutexes and so forth. In lecture, we'll also talk about one other coordination mechanism, a barrier, so we'll get to that in just a second. But you'd want to think carefully as you divide up the work in the matrix amongst threads. There are a lot of different ways to do this. Two of the common ones are give some number of rows to the first thread, give more rows to the next thread, give more rows to the next thread that's there, or give some number of columns to the first thread that's going to work, give some middle columns to the next thread over, give the remaining columns to the third thread that's going to work there. Each of these two has some implications on what the memory pattern of access for those threads is going to be. And so just bear in mind then that you'd want to avoid memory strides there, and this may govern some particular access pattern associated with threads. So that's good. There are right and wrong answers here, so you may need to experiment a little bit, but think carefully about that stuff and use your best judgment. If you seem to be stuck at some point, then try inverting this and seeing if it works better. Now, since the threads are going to be coordinated or need to sort of work and say we're all working to compute this average vector here and the standard vector here and to modify all these elements in the matrix here. If you find that there's some common stuff like everyone needs to contribute in order to calculate what the average is, then you'll want to make use of a mutex to coordinate access to those things. In fact, that's a required part of the project to demonstrate you understand how to access shared data using a mutex to protect it. Two threads are in competition to simultaneously change some elements. This is a recipe to screw things up, so try to make sure of that. But keep the code between the mutex, protect this area and then unprotect it by unlocking the mutex. Try to keep that as short and sweet as possible, as only one thread will be able to execute the code that's there at a time. If that's confusing to you, look carefully at the demonstration of this in Lab 12, as that will serve as a wonderful template for what's to be done in this part of the code. Finally, one thing that doesn't show up in the lab but is useful to know about is that there are, in some versions of algorithms that would solve this, a need to coordinate to say every thread has to be finished with this part of the code first before any thread should proceed forwards. And so over here, I'm going to blow this up just a little bit more so you can see, is an example of that. Suppose I was executing some algorithm where I start up a bunch of threads, so pthread create, and I pass in these workers over here. And the nature of the work is such that there's a part A, a part B, and a part C. And the way that I've divided the work amongst the thread workers is that before I could do part B, all of the part A has to be finished by all threads. The best way to facilitate this is to set up a little barrier data structure. This is provided as part of the pthreads library, and then pass maybe some reference to that, preferably not a global variable, but that's an easy way to do it here, is then to say, here, all threads call this pthread barrier weight. which is to say if there are 4 threads running, then everyone has to arrive at this point before any of the 4 threads proceed into this next section of the code. And before they proceed to the C section over here, again, wait, as in all 4 have to arrive at this point before anyone goes forwards. Supposing thread 3 is the fast one and arrives here first, it'll just sit on its hands for a little while until the other threads catch up. And typically this is an OS facility that says, oh, thread 3 arrived here, and the other 3 threads, they are still finishing up, and so the schedule will just say, we're going to put thread 3 on hold for now. Doesn't occupy any CPU resources, it just sits there and sleeps until the other 3 threads arrive, at which point it will schedule the thread 3 again to say, now everyone has arrived here, all the work that needs to be done is finished, now you can all proceed safely to the next one. I'll talk a little bit about this in lecture. It's not a hard thing to understand, but in my own implementation of some versions of the optimization, I found this to be an extremely useful thing to do because unlike mutexes, which don't guarantee everything is there yet, barriers will efficiently cause threads to pause until everyone else catches up with them, which makes coordinating activities a lot easier if you need some of the work to be finished. Now, there are ways around this. For instance, you could intersperse, there's a worker A and a worker B and a worker C. You could create these and then join them and then start up worker B and then join those and then create a worker C. But this is a lot slicker and allows then you to start up the threads and not have to wind them down with joins and restart them and so forth. So put that to good use if you find a need for it there. Just a couple other things here, and we'll look at some code for this. If you are implementing this, you should use a mutex at some point. This is an important part of the game, and it's a goal of the class that you learn a little bit about coordinating multiple processes or threads, and so a mutex is great for this. Should break anyone's brains. If you're coming from CMC 132, you've probably already done similar things. And as well, avoid global variables. So this is a really common tactic that even I am guilty of occasionally on threads. But there's a much better paradigm to doing this that makes this kind of code less obtrusive and more library friendly in that way. We'll talk about it in lecture, and it's also demonstrated in lab that within each thread here you pass in an argument that's a context of some kind that has all the communication variables that are needed by the thread. So we just take this thing and put it into some kind of a struct and have instances of that struct that are passed to each of the threads that are over here. If you work through Lab 12, that pattern will become very apparent. So you'll lose a little bit of credit if you use global variables here. So make sure that you sort of cognizant of that. And finally, respect the thread count. Make sure that if someone says start at most 3 threads, you don't actually start like 8 of them instead. That's not something, it's maybe easy to do, but this is sort of, we can't judge this except by hand by looking at this, where it's like, oh, over here I was trying to cheat the benchmark. So when it said use 1 thread, I actually used 3 threads or something like that. If a grader sees that, then we'll penalize that. And I haven't had anyone actually do that before, but it stands to reason that as you gamey students are looking for ways to eke more points out, then that could be one way. Just don't do that. Honor that variable there. Oh, I should mention, you can assume that the number of threads is relatively small compared to the size of the matrix, and examples of that show up in the benchmark that at most we'll have 4 threads, and you've got 1,000 rows and 2,000 columns here. Larger sizes go even bigger than that, and so it makes sense to assign large portions of the matrix to each of the threads, rather than assume like, oh, there are many threads that are each going to get their own individual element of the matrix or something. My general experience in parallel computing is that almost never happens, and so you're much better off sort of assuming that the amount of work to do is much larger compared to the computing elements, the threads that you'd have there. Now, if you're interested in doing some makeup credit, there are some suggestions for additional optimizations that you might try to greatly exceed the 35 points that are available there. I think there are tiers that you could get 40 if you do a little bit more optimization, and up to 45 if you do a lot more optimization. And there's some suggestions in here, the places you might look. For instance, Brian O'Halloran, Chapter 5 has some of the additional optimizations that are optional for you to look at there, but might earn you some makeup credit here. Let's look at some code because all this maybe make a little bit more sense. So the code associated with this is in this call norm optim stuff over here. It's worthwhile to first look at this baseline version over here. And it's described in the spec, but I should mention it again here. There are a series of macros like mget and vset and so forth that make it a little bit easier to work with the matrices involved. So mget here would go fetch an element out of a matrix. Vset would set within a vector. Average, in this case, is one of the arguments up here. The jth element to whatever this value is. It's the average I just computed in the step above this over there. So use those. There's mget, mset, vget, and vset here. To access those, it will adhere then to the structure of the vector and mat matrix T structs that are in the header. One minor note on that. It improves efficiency just a little bit in some cases for the rows of a matrix to be aligned at byte 16 addresses. You might remember from our assembly discussion that certain things on x86-64, like function calls, work better if the stack pointer is aligned at a 16-byte boundary. That's true as well for certain efficient floating point operations, loads and stores, and vector adds and so forth. So there's a little bit of disparity here between the matrix, its actual size and its purported size, number of rows by columns. So just make sure to use the macros in some way or really understand what you're doing here if you try to break out of the macros. And I should mention those macros are defined here. They look sort of like functions, but it's really just this code is going to be inserted in place. A function call here might be a little bit more versatile, but it would be way, way, way slower. And so having this code inserted at this point rather than devolving to a function call means all the registers that are within this function are still available. It's generally more efficient, so it's what we'd want in this case. But macros are just terrible to write, and perhaps you'll get away in life without ever writing them, but I thought I was in that position and now write them all the time. So C's macro facility is not great, but no matter. Okay, so this is the baseline version over here, and the version that you were supposed to write of this call norm routine, it is, there's a provided version in here in call norm optim. A couple things, when you actually get your stuff finished, then you should insert your own little version of that table of what your performance was there. It makes it easier. But here's the provided version. It doesn't do squat. It is arranged in a structure that's useful to know about. So the call norm optim, this is the one that's called, it just dispatches to this CN version A. There's also a version B here. They don't do anything, but this lays out a structure where, oh, if I get some version A done right here, that's reasonable. And I'm going to start tweaking it, but I don't want to sort of forget what performance I got for this one. Just make a copy of it, call it version B, and then change this call to version B down here. And keep changing that so that you can always revert back to an earlier, better performance, perhaps commenting on this as like, oh, this version got 5.0 out of 35 points or something like that. I mean, right now this is going to get 0 out of 0 points, but we'll fix that readily. So this is specifically set up then to make it easy to sort of have several different versions, experiment with them, and then commit to one that you think is best down here. Just make sure to do that. Like the first problem, if I jump over to my shell, then you can do a make. Let's see, test prob 2. This will, produce all incorrect output so far. And importantly, the call norm benchmark. This is the one that runs. Over here, I'm going to get all kinds of errors over here. And that's because my do nothing routine, it constantly produces, since it does nothing, none of the stuff is actually optimized over here. And so I'm just getting a long litany of error messages over here instead. Now, one way I can fix this is as follows. Let's just take the baseline version. We'll copy that. I'm going to make this here, and I'll rename this one version A. I can get rid of this now. And I think that's the one that's called here. Okay, so I'll jump back over the shell. I'll make this. Let's see, implicit declaration, function CN ver A. Did I got the names wrong, didn't I? Oh, see, I call it call norm. And let's make this CN. And I'll leave a comment here, copy of baseline. Like that. I'll make this then. Let's see. Let's see. Too many arguments. Oh, gosh, shoot. I forgot. It takes an extra argument up here, so let me just give that one that's here. Int thread count. Extra parameter down here that the baseline version doesn't take, but need to pass that over here. So that's saved. I'll make this thing, so I compile, and now I can run the benchmark, and it'll, give me 0 points because I'm going exactly as fast as the baseline. In fact, I'm just running the baseline again, so I should get almost no credit for this. However, hey, I've got a working version, and that's better than nothing. In that case, I'll probably pass most of the tests associated with this, but since I get the bulk of the credits for the performance evaluation, that's not going to do me a ton of good. And so this is sort of one way to start. The next thing to do then would be, let me try and take some of the things that I learned from like Lab 12 about optimizing the memory access pattern of this thing and plop it down here in a version B. Change this over to version B, and voila, I'll have maybe some slightly better performance over here. Optimizing the memory performance is going to get you a long way on this, and so do spend some time on that. It's low-hanging fruit in order to get points. One other thing I should mention here, since I ran this on my home computer rather than one of the odd-numbered graces, I get the same set of warnings here as you would get if you ran on any other host that is no good. So keep that in mind as well. It's fine to do home development, try some ideas out, and generally I'd expect the performance on your home computer to be, some linear sort of scaling of what's on Grace on those odd nodes. So if you get better performance on your home computer between version A and version B, then I'd expect version A to give the same improvement to show up in some way on the Grace nodes. Not always, but feel free. It's more convenient to develop at home if you already got that regime there. But aside from that, then I think we are set on this. Happy hacking all. This will be the last one. It's not that bad of a project according to historical precedent, but hopefully you will learn quite a bit from it. And man, does it ever feel good to optimize some code to just kick the snot out of like some baseline version. I'm now going 16 times as fast, and that feels good in a very CS specific way. So take care all, and I'll see you in lecture.